Thanks everyone for coming. This is the beginning of the afternoon sessions. And the first talk of the session will be on the limitations of variational quantum algorithms and is given by Daniel França.
Okay. Sorry to interrupt the applause. So this is based on joint work with Giacomo de Palma, Milad Marvian, and Cambyse Rouze, who's in the audience. So any imprecisions or mistakes in the slides are his fault. Talk with him afterwards. And this was also recently published, I think last week or something like this. So this talk will be about finding ground states or approximate ground states of classical Hamiltonians. So think about, for instance, your favorite Ising model. And, you know, it's well known that you can encode several combinatorial optimization problems into finding the ground state of such an Ising model, say, max-cut. Right? And the question is whether we can use near-term devices, near-term quantum devices, to find good approximate solutions to this problem. Now, near-term quantum devices come with two limitations because we do not expect them to have error correction, so there will be errors happening in the device as we implement operations. And this means that we can either implement very shallow circuits for which the amount of noise present is negligible, or we can implement deeper circuits at the expense of having a non-negligible amount of errors. And the question is, how do these two things actually limit the performance of quantum devices to find interesting solutions to such combinatorial optimization problems? And in this work, we give some toolkit to analyze this problem through the lens of optimal transport and some new concentration inequalities for outputs of very shallow or noisy quantum circuits. So just so that we're all on the same page, we were talking about quantum algorithms like QAOA. So, you know, you start with the plus state, you apply a bunch of parametrized unitaries, and hopefully by not applying too many of them, when you measure the output, you already find good solutions to the problem you care about. So this is the sort of algorithm we're looking at. You apply a bunch of unitaries, then you measure, and you hope to find something interesting. Now, as I mentioned before, noise will play an important role in what we're going to talk about, but I'm going to talk only about the case of the simplest noise model you could think of, namely local depolarizing noise with a certain depolarizing probability P. Most of the results I'm going to present actually generalize to other noise models. There are some caveats here and there, but for simplicity, I'm just going to focus on this very simple noise model. And although previous work already looked at which depth you actually lose quantum advantage under these simple noise models, this was only an expectation. And now in this work, we also derive concentration inequalities. And we also can, using these tools, analyze the limitations imposed by shallowness, not only noise. Now, so instead of, again, applying these layers of unitaries, what's going to happen is that every time we apply a unitary, we then also apply the associated noise map. So this is our simple noise model, and in this case, T will just be a bunch of local depolarizing noise channels. Okay, so a quantity that will be important to discuss our results will be the so-called Lipschitz constant of an observable. This was introduced by De Palma and co-authors in 2021. It was also a QIP talk. And roughly speaking, this Lipschitz constant of an observable H quantifies how stable this observable is to local perturbations. So essentially, what you're trying to see is by how much the expectation value of this observable H can change if you look at states that are the same once you throw out one qubit. Okay, and the nice thing is that it recovers the notion of the Lipschitz constant of a function on the Boolean cube if you pick your metric as the Hamming distance. And for instance, if you just consider an Ising model on a d-regular graph, then this Lipschitz constant is at most 2D, because if you have states that are the same on up to 1 qubit, right, then only the terms acting on that 1 qubit will be able to change this expectation value, and there are at most D many of them. Okay, and there are many different forms of concentration considered in the literature. They're all related to 19th century mathematicians. Concentration inequalities, of course, deviate, measured by how likely it is that a given random variable deviates significantly from its mean. So for instance, the three that are relevant in this talk are the Gaussian, after the slightly smug grumpy Gauss over here, which gives some sort of exponential concentration around the mean. A slightly weaker form, but still exponential, is by of course, Laplace over here, and Markov here, the quadratic. But this one is different because it only gives us a polynomial tail, like a polynomially small probability of deviating significantly. And the intuition is that the more this distribution is behaving like an IID, random variable, the closer it is to satisfying, say, Gaussian concentration. Now, what is the connection between limitations of these algorithms we were talking about before? Now, look, if you consider, for instance, QAOA or, say, adiabatic quantum computing, you usually start, for solving combinatorial optimization problems, you usually start at the plus state. And when you measure that in the computational basis, what you're going to get is just some uniformly distributed bits. Okay? Well, it turns out that if you then look at an Ising model, you'll see that the energies you're going to observe will mostly be of this order. And it turns out that there are efficient classical algorithms that will find much better energies. So this means that, of course, which isn't surprising, that random guessing isn't a great strategy. More sophisticated classical algorithms can give you much better energies. So this is where we start, right? And as we are applying noise and more noise, this is the polarizing noise, so the outcome of the circuit starts to look like a maximally mixed state. And in the limit of as much noise as you can think of, you, of course, recover it exactly. And then, again, when you measure in the computational basis, you'll just get the uniform distribution again, which also has Gaussian concentration. So we see that on both extremes, like at the very beginning and that after you applied a lot of noise, we expect these sorts of energies. And classically, you can get this, which is much better because we're trying to minimize this function. So yeah, the question is, what happens in between? Can we actually move to the more interesting regime? Okay, and it's important to say that we here are not interested in necessarily talking about how difficult it is to simulate these circuits, because it could very well be the case that it's very hard to simulate what's going on in the device, but it's still producing like useless outputs compared to a classical solver. You only want an approximately good solution, right? And we also want to be able to benchmark against heuristic solvers. So maybe you have like this very nice algorithm, you can prove it's good, but you see it performs well in practice, and you want to be able to give like a back of the envelope estimate whether it makes sense to potentially improve what you're doing with a noisy quantum device. And just to be clear about what I mean by loose quantum advantage, what I mean is that if we can find a classical algorithm that outputs a certain energy EC, and if we let EQ be the energy of the output of this quantum device, we'll say that we lost quantum advantage if the probability that the output of the quantum circuit is smaller than the classical one is exponentially small. In this paper, we also take a look at how these conclusions change with error mitigation techniques and also adiabatic quantum algorithms instead of the circuit model, but I'm not going to have time to get into that. Okay, so let's just quickly go back to the setting of like measuring the uniform distribution. So more precisely, you can show the following concentration inequality. If you're for any traceless observable H, if you measure H in the eigenbasis, any state in the eigenbasis of H, the probability of a deviation of order epsilon times n from 0 is upper bounded by this. Okay, so this is just saying that if you get random bits, this is how the distribution concentrates. And as I mentioned before, there are classical algorithms that will spit out energies of order n times the Lipschitz constant of H, whereas random guessing will constrain you to like square root of n. So the question now is, how do we transfer what happens when we get like a lot of noise, so we're effectively in the maximally mixed state, to the case where we have just a bit of noise? Because we expect that once we pump more and more noise to the system, it's going to have similar concentration properties as the maximally mixed state. But when does this transition happen, and how do we quantify it? And it turns out that a good way of doing this is by measuring the distance between the output of the state of the circuit and the maximally mixed state with, for instance, a sandwiched Renyi divergence. It has already a lot of applications in quantum information theory, like strong converses, and it's not difficult to show that you can easily transfer, like obtain upper bounds on, for instance, the overlap of a state with a POVM in terms of both the Renyi divergence between any other state and the probability of observing that POVM outcome on this other state, sigma. So in some sense, if you have two states that are close in the sandwich Renyi divergence, then you can also transfer the probabilities of these outcomes. And in particular, if we combine this with this Gaussian concentration I measured before, we see that this log trace E sigma, if you have something like the maximally mixed state that satisfies Gaussian concentration, well, then you get an inequality like this one. So you have something that is like exponentially small over here, and you have this Renyi divergence over here. So for instance, if you think as this as the projector onto the good input output strings, so like this is the support on the strings that are better than the classical algorithm, we see that as long as this term here loses to this one, then it's exponentially small, we're going to find anything interesting. So, for instance, if we pick this thing to be epsilon squared over 8, for instance, then we're going to lose against this one, and then there will be no exponential advantage anymore. And it turns out that it's quite, there are standard tools to quantify how fast this happens. So, for instance, there are tools through contraction coefficients of quantum channels. And, for instance, for the depolarizing channel, one can show that this Renyi divergence will contract by a constant factor after a constant layer of noise, of channels, of unitaries, that only depends on the local noise rate, regardless of the circuit you're actually implementing. So we see that as long as the depth is large enough, such that it's comparable with the local noise rate, it's exponentially unlikely you'll see any interesting string as the output of the quantum circuit. But there's also the limitation imposed by shallowness. And concentration inequalities also help you to say that you cannot prepare certain states through shallow circuits, okay? And this is not, you're not the first ones to observe this. And for instance, consider the case of the G8Z state to see why this is the case. If you measure an observable like Pauli Z on each qubit, then the expectation value is 0, but you're always going to observe the two extremes, like minus n and n. So this thing doesn't concentrate at all. So you know that if you have a family of circuits and the outputs all concentrate, then you cannot prepare the G8Z with this family of circuits, because otherwise you'd have to observe an outcome distribution which does not concentrate at all. And so we also derive some new concentration inequalities for the outputs of shallow circuits. So in the published version, you'll only see what we call a Q-infinity Poincaré inequality, which we show for all product states, which gives a polynomially decaying bound on the tail of the output distribution for product states. And in upcoming work, we were able to show exponential concentration. There's some other activity in this direction going on like understanding concentration properties of outputs of shallow circuits. But this was only for product states. But then using this whole machinery of the Lipschitz constant, it is possible to show that if you consider the growth constant of a circuit, which is essentially by how much the circuit can increase the support of any one qubit observable. Okay, so for instance, in this case here, like we have this one qubit observable over here, and this circuit will increase in principle the support of this observable to all of these qubits. So the growth constant will be 6 in this case. So using this notion of the growth constant, we can also show a concentration inequality for outputs of shallow circuits. And by how much you concentrate depends on this growth constant. And in particular, if you have a constant depth circuit, then this growth constant can also only be a constant, right? Because you only map like a constant number like this. Every qubit will only talk to a constant number of other qubits. And this in particular implies that you cannot prepare G8Z-like states, right? Unless, for instance, this growth constant is proportional to the whole system. So all qubits have seen each other. Now, what is the connection of this to optimization algorithms like QAOA? Well, note that in principle, you can find very good solutions to these optimization problems with depth 1 circuits, right? You just have to flip each one of the qubits at the right place, because, I mean, these are like these are like classical states you're looking at, and find the ground state. So in principle, even with a depth 1 circuit, you could find the exact ground state, but algorithms like QAOA or annealing, they have some inherent symmetries to them. So for instance, the initial state is the all plus state, and the Hamiltonians we involve with are either all X or like products of Z, and they all commute with this observable over here. You have this Z2 symmetry. So this means that throughout the computation, you only have states that commute with this thing. As the algorithm has these inherent symmetries, they cannot do anything, and this constrains their performance. And in previous work, they were then able to construct instances of max-cut where all the ground states that also satisfy this sort of symmetry are G8Z-like, in the sense that they have output distributions that do not concentrate when you measure them on a computational basis. So by using this observation, we were then able to improve with our techniques these previous results, and we obtained like simpler proofs and also better constants. And in particular, we were able to show that for algorithms like QAOA, you need at least log n. I mean, this was already known, and there are other ways of doing it, but you need at least log n depth. What wasn't known, I guess, is that this also holds for the noisy case, and again, better constant, easier proofs. But if we go back to what I talked about before, in the case of noise, we see that the depth at which the noise kills you is constant. The depth you need to go to see interesting strings for these instances of the problem is logarithmic in n. So for these sorts of problems, we see that there is no quantum advantage on a noisy quantum device, because the noise will kill you before you can actually get to the interesting string. So at all points during this computation, the probability that you see an interesting string is exponentially small. And with that, I'd like to conclude and thank you for your attention.
Thanks a lot, Daniel. We have 5 minutes for questions, and we also have a cube mic that will be thrown to you. So just for the excitement, you should ask questions. Go ahead.
Yeah. Okay, thanks very much for the nice talk. I wonder, in your results, it seems the bonds you obtain depend on the Lipschitz constant. So I wonder, do you have, why it's Lipschitz? Do you have any, simple intuition behind this?
Why the Lipschitz constant?
Yeah, why Lipschitz?
Can you just repeat the question and then answer it?
Yeah, okay. So I'm not sure I understood it as well because there are people coming in. So I think the question was, if I have some intuition, why the Lipschitz constant is important in this proof?
Yeah, right.
Okay, thanks. Well, I guess it's what pops up in let's say, the classical version of these things we're trying to do. So usually it's like... if you want to prove concentration inequalities, it's usually a very simple way or the best way of doing it. And as we're kind of trying to follow this program of getting quantum versions of these classical concentration inequalities, it's also something that we want to incorporate because then, sometimes your life gets easier because you can import some ideas. But that's a lazy answer, I guess, yeah.
Okay, one more question for the people who are leaving. Just be a little bit more quiet because there's a lot of noise. It's an old amphitheater. So second question, yeah.
Hi, thanks for the presentation. I have a question for the noise model, because here you only guessed that we have a simple noise model with this local depolarizing errors. Do you have an idea about the similar, justification of results if we add some other kind of more complex noises?
Yes, great question. So, so the result works. The same things work as long as that you have a product channel and it's not it's not converging to something pure. So, for instance, I introduced the sandwich Renyi divergence for the maximally mixed case state. It's not important because everything commutes anyways, but if you have, for instance, say you're converging to a product state, as long as it's not pure, then essentially the same conclusions hold. And I would expect that the conclusions shouldn't change too much if you're converging to a pure state, but to be honest, I don't know how to prove it.
Okay, we're going to take 2 more questions, the first one and the second one over there.
Hi, thanks for the nice talk.
I
was wondering, so you're bound for the shallow end. It depends on basically this GHZ likeness of the state that's being prepared, right?
Mm-hmm.
So I was wondering whether you have an intuition whether this is an artifact of the proof and in principle, whether you expect basically, these shallow circuits to be useless as well for other states, or whether you think it's there's an actual phenomenon there.
I see. So as I mentioned, there are other proofs that show that in the noiseless case, you don't you need to go to log n depths. They don't need this sort of symmetry. So I expect that generally speaking, as long as you haven't made sure that every qubit has talked to every qubit, it seems like these algorithms can't do much. So I would expect it to be a more general thing. Yeah.
Okay, one last question.
Hey, thanks for the talk. I think it's really cool that you can use these concentration inequalities to show something about the performance of QAOA or such algorithms. So I'm curious whether you think the same sort of techniques might be useful for a situation where you allow for classical measurement and feedback in the circuit.
Yeah,
because
sure.
In that case, I believe you can prepare the GHG state in like constant depth, right?
Yes. So that's something we are. I would like to solve. So there are ways of preparing GHZ states with constant depth, but then you have to have classical feedback, as you mentioned, and I would expect that there is some sort of trade-off between how many measurements you have to make and things like that. So I would assume that the same sort of bound still holds, but I don't know how to show it, and it's something I'm like working on right now. But yeah, it's a
All right, cool.
great
Thank you.
All right, let's thank Daniel again.